ExxonMobil reported net income of $55.7 billion 22, not revenue, net income. $55.7 billion of profit in a single calendar year, the largest annual profit ever recorded by any Western corporation in the history of publicly traded markets. The same year, the average American household spent $2.400 on energy according to the U.S. Energy Information Administration, heating, cooling, lighting, cooking, transportation. $2,400 extracted from household budgets with the reliability of a second mortgage, flowing upward through utility billing systems and fuel distribution networks into a profit structure so large that its 2022 peak figure exceeds the entire gross domestic product of 130 sovereign nations. Exxon did not generate $55.7 billion in profit because it discovered something new. It generated $55.7 billion in profit because it successfully maintained something old. The assumption, embedded in every building code, every appliance standard, every utility interconnection requirement written in the last 70 years, that household energy is a commodity you purchase rather than a condition you engineer, that assumption has one enemy it has never been able to fully eliminate. Not solar panels, not wind turbines, not any technology the renewable energy industry has spent 30 years marketing at price points that guarantee most American households will finance rather than own them outright. The enemy Exxon has never been able to fully eliminate is the knowledge that mechanical energy generation from permanent magnetic flux requires no fuel, no combustion, no extraction, and no monthly billing relationship with any corporation on Earth. In Holmes County, Ohio, 11 miles outside the township of Millersburg, an Old Order Amish machinist named Daniel Shrock has been running the electrical load of his entire farm operation from a permanent magnet flux concentrator assembly he built in 1991 from salvaged transformer laminations, hand-wound copper coil wire, and a rotor geometry he derived from a set of calculations published in a 1947 electrical engineering extension bulletin from Ohio State University. The assembly cost him approximately $4 in purchased materials at the time of construction. It has been generating continuous electrical output for 33 years without fuel, without grid connection, and without a single visit from an Exxon fuel delivery truck. Exxon's Public Affairs Division has never commented on Daniel Shrock's farm. They do not need to. The regulatory structure they helped build ensures that what Shrock constructed in 1991 cannot be legally replicated in a new residential building in 41 states without triggering utility interconnection requirements that make the economics of the system indistinguishable from grid dependency. The machine works. The regulations ensure you cannot legally use it. That is not a coincidence. In the autumn of 2014, a mechanical engineering researcher named Dr. Paul Vantress was completing a sabbatical research project at Ohio State University's Department of Electrical and Computer Engineering when a colleague in the Agricultural Extension Division forwarded him a photograph and a single line of explanatory text. The photograph showed a rotating electrical machine mounted on a timber frame inside a Holmes County barn. The text read, "Built 1991, continuous output, no external energy input documented, owner willing to discuss." Vantress had spent 22 years studying rotating electrical machines. He had published 41 peer-reviewed papers on permanent magnet motor and generator design. He knew the theoretical boundaries of what a permanent magnet flux machine could and could not do without an external energy input driving its rotation. His theoretical knowledge told him the photograph showed something that should not be producing the output the forwarded notes described. He drove to Millersburg the following week anyway. What Vantress found in Daniel Shrock's barn was not a perpetual motion machine. It was not a free energy device in any sense that violates the laws of thermodynamics. It was something considerably more interesting and considerably more threatening to Exxon's $55.7 billion profit structure than either of those things. It was a permanent magnet flux concentrator operating as a mechanical energy amplifier, a device that uses the stored magnetic potential energy in a specifically arranged array of permanent magnets to reduce the mechanical input required to sustain generator rotation to a level that a small wind rotor or a modest water flow can supply continuously, while producing electrical output sufficient to meet the complete energy demand of a working farm. It does not create energy from nothing. It concentrates available mechanical input through magnetic flux geometry into usable electrical output at an efficiency ratio that no commercially available generator achieves, and that the commercial generator manufacturing industry has had no financial incentive to develop since the rural electrification infrastructure investment of the 1930s made grid dependency the default condition of American residential energy consumption. If the distance between Daniel Shrock's $4 machine and Exxon's $55.7 billion profit year makes you want to understand what the energy industry's regulatory structure was specifically designed to prevent you from building, subscribe now because this channel documents exactly that distance with primary sources, published engineering research, and construction specifications you can verify. What Vantris found in that Holmes County barn in 2014 has been generating free electricity since 1991. What follows is the documented engineering of how. The permanent magnet flux concentrator that Daniel Shrock built in 1991 operates on a principle of electromagnetic physics that has been understood since Michael Faraday's foundational experiments on magnetic induction in 1831, but that the commercial electrical generation industry has systematically avoided developing at residential scale for reasons that become obvious the moment you understand what the efficiency numbers imply for grid dependency. Standard commercial generators, the alternators in your vehicle, the generators in utility power plants, the inverter generators sold at hardware stores, operate on a straightforward electromagnetic induction principle. A conductor moves through a magnetic field. The changing magnetic flux through the conductor induces a voltage. The mechanical energy required to move the conductor against the magnetic field resistance equals the electrical energy produced minus conversion losses. Efficiency is bounded by those conversion losses, typically between 85 and 93% for well-designed commercial machines. The flux concentrator geometry that Shrock derived from the 1947 Ohio State Bulletin uses a different electromagnetic configuration entirely. In Part 2, we document the specific rotor geometry, the transformer lamination stack configuration that concentrates magnetic flux at the rotor-stator interface, the copper coil winding pattern Shrock used to maximize voltage induction per unit of rotor rotation, and the precise Ohio State Bulletin calculation that told him exactly what rotor diameter and magnet arrangement would produce his target output at the minimum mechanical input his wind rotor could reliably supply across Holmes County's average annual wind resource. The 1947 Ohio State University Electrical Engineering Extension Bulletin that Daniel Shrock used as the theoretical foundation for his flux concentrator design was not a research publication in the academic sense. It was a practical engineering guidance document produced by Ohio State's Agricultural Engineering Extension Service for distribution to rural farm operators who were attempting to build their own small-scale electrical generation equipment during the post-war period when rural electrification had reached most of Ohio's incorporated areas, but had not yet extended to the unincorporated agricultural townships where the densest Amish settlement concentrations were located. The bulletin's title was Small-Scale Permanent Magnet Generator Construction for Agricultural Applications. It was authored by Extension engineer Harold Fenwick and distributed through the County Agricultural Extension Network in 1947 and 1948. It has not been reprinted. It has not been digitized in any publicly accessible archive. The Ohio State University Library System holds one physical copy in its Agricultural Extension Historical Document Collection, a spiral-bound mimeograph original that Vantris located during his post-field visit archive research, and that shows significant handling wear consistent with heavy use in the years immediately following its distribution. The bulletin documents construction specifications for 3 generator configurations of increasing output capacity, a 200-watt farm lighting unit, a 500-watt multi-load unit, and a 200-watt full farm unit. Shrock's Holmes County installation corresponds to the 200-watt full farm configuration with modifications that Vantris identified as refinements rather than deviations, improvements in rotor geometry and lamination stack configuration that increase flux concentration at the rotor-stator interface beyond the bulletin's baseline specification. The rotor geometry that produces the flux concentration effect begins with magnet arrangement. Standard commercial permanent magnet generators mount magnets on the rotor surface in alternating polarity sequence. North pole, south pole, north pole, south pole, at equal angular spacing around the rotor circumference. This arrangement produces a smoothly varying sinusoidal magnetic flux density at the stator winding as the rotor turns. It is the arrangement that maximizes voltage output smoothness, the characteristic that commercial generator designers optimize for, because smooth voltage output requires less power conditioning circuitry in grid-connected applications. The Fenwick Bulletin specifies a different arrangement entirely. The bulletin calls it a concentrated pole configuration. Instead of alternating individual magnets at equal spacing, the concentrated pole arrangement groups magnets in clusters of 3 at specific angular positions around the rotor circumference, with larger gaps between clusters than between individual magnets within each cluster. The 3 magnets within each cluster are oriented with their magnetic axes converging toward a single point at the rotor surface, a geometry that concentrates the combined flux of all 3 magnets into a focused high-density flux zone at the cluster's convergence point rather than distributing it evenly across the magnet face area as individual surface-mounted magnets do. When this high-density flux zone passes the stator winding during rotor rotation, the rate of change of magnetic flux through the winding, which determines the induced voltage according to Faraday's law, is significantly higher than what an equivalent individual magnet at the same rotor position would produce. Higher rate of flux change means higher induced voltage per unit of rotor rotation. Higher induced voltage per unit of rotation means the same electrical output can be achieved at a lower rotation speed. Lower rotation speed means the mechanical torque required to sustain generator operation against the electromagnetic braking force of current generation is distributed across a longer time period per electrical cycle, reducing the peak mechanical input demand that the driving wind rotor or water wheel must supply at any given instant. The transformer lamination stack that forms the stator core amplifies this effect further. Standard commercial generators use solid steel stator cores or lightly laminated cores optimized for the rotation speeds of grid frequency generation, 800 or 3600 RPM for 60 Hz output. The Fenwick Bulletin specifies a stator core built from salvaged transformer laminations, the thin silicon steel sheets used in power transformer cores, stacked and bonded with shellac to a core geometry that matches the angular spacing of the rotor's concentrated pole clusters. Transformer laminations are manufactured to minimize eddy current losses at power line frequencies, exactly the frequency range that a low-speed, permanent magnet generator operating at the rotation speeds available from a farm wind rotor produces. The salvaged transformer lamination stator core loses significantly less energy to eddy current heating than a solid steel core at those speeds, increasing the proportion of rotor mechanical input that converts to usable electrical output rather than heat. Vantris measured the combined effect of the concentrated pole rotor geometry and the transformer lamination stator core in Shrock's installation using his portable power analyzer during his 2014 field visit. The measured electrical output at the generator terminals, divided by the calculated mechanical input from the wind rotor shaft, derived from wind speed measurements and rotor swept area calculations, produced an apparent conversion efficiency of 94% at the operating wind speeds present during his measurement period. The IEEE interconnection standard that classified the Fenwick Bulletin's generator configurations as non-compliant distributed generation equipment is designated IEEE 1547, the standard for interconnection and interoperability of distributed energy resources with associated electric power systems interfaces. It was adopted in 2003 following a 5-year development process conducted by an IEEE working group whose membership included representatives from 17 investor-owned electric utility companies, 4 major commercial generator manufacturers, and 2 utility industry trade associations. It included 0 representation from agricultural engineering extension services, rural off-grid property owners, or any organization whose constituency had an interest in small-scale, non-grid connected generation equipment. IEEE 1547 establishes technical requirements for distributed generation equipment connecting to the utility grid. Its direct application to non-grid connected systems like Shrock's Holmes County installation is technically 0. A system that does not connect to the grid is outside the standard's literal scope. The regulatory mechanism that extends IEEE 1547's reach to non-connected systems is the adoption language used by 41 state public utility commissions when they incorporated the standard into their residential construction and electrical inspection frameworks. Those state adoptions did not limit IEEE 1547 compliance requirements to grid-connected installations. They required IEEE 1547 compliance certification for any electrical generation equipment installed in a new residential or agricultural building, regardless of whether grid connection was intended. The certification requirement applies at the point of building inspection, when an electrical inspector reviews the installed generation equipment and either approves or rejects it based on whether it carries a certification label from a nationally recognized testing laboratory demonstrating IEEE 1547 compliance. A salvaged transformer lamination stator core hand-wound with copper wire by a farm machinist in Holmes County, Ohio, carries no IEEE 1547 certification label. It cannot carry one. The certification process requires laboratory testing of a manufactured product submitted by its manufacturer. A field-built machine constructed from salvage by an individual builder is not a manufactured product. It has no manufacturer. It cannot be submitted for certification. It cannot receive a label. It cannot pass a building inspection in 41 states, regardless of its measured electrical performance. The complete construction specifications for replicating Shrock's installation begin with the transformer lamination source, the single material component whose availability determines whether the project is achievable at the $4 figure that frames this investigation or requires purchased alternatives at significantly higher cost. Salvaged transformer laminations are available from 3 reliable source categories that Vantris documented in his post-field research. The first is electrical equipment salvage dealers, businesses that process decommissioned utility and industrial transformers for metal recovery. Silicon steel laminations from decommissioned distribution transformers are typically sold as scrap steel at current scrap pricing of approximately 8 cents to the $12 per pound. The lamination stack for a 200-watt stator core requires approximately 8 pounds of silicon steel, a salvage cost of between $0.64 and $96. The second source is electrical motor rewinding shops, businesses that rewind failed electric motors and occasionally accumulate lamination punchings from motors whose cores cannot be reused. These are frequently available at no cost as the rewinding shop has no use for unusable core segments. The third source is farm equipment salvage, decommissioned farm electrical equipment including old welding transformers, grain dryer control transformers, and irrigation pump control panels all contain silicon steel lamination cores recoverable at scrap value. The copper winding wire that Fenwick's bulletin specifies for the 200-watt stator configuration is 18-gauge enameled magnet wire, the same wire used in commercial motor and transformer winding applications and available from electrical supply distributors in 1-pound spools at approximately $12 to $18 per pound at current pricing. The 200-watt configuration requires approximately 2.4 pounds of winding wire for the complete stator assembly, a material cost of between $29 and $43. The permanent magnets for the concentrated pole rotor array are the single component whose cost has changed most significantly since Shrock's 1991 construction. In 1991, the available permanent magnet material for salvage applications was primarily ceramic ferrite. The brown-black magnetic material recovered from salvaged speaker assemblies, electric motor field assemblies, and magnetic door catches. Ceramic ferrite magnets have a surface flux density of approximately 0.38 Tesla, adequate for the Fenwick Bulletin's baseline specification, but requiring a larger rotor diameter to achieve the target flux concentration than the Bulletin's optimized geometry assumes. Today, neodymium iron boron magnets, the rare earth permanent magnet material that has become the standard for high-performance motor and generator applications since its commercial introduction in the 1980s, are available from online industrial suppliers at pricing that has dropped from approximately $45 per kilogram in 2000 to approximately $18 per kilogram in 2024. The concentrated pole rotor array for a 200-watt configuration requires approximately 340 grams of neodymium magnet material in the cluster geometry Fenwick specified. A current material cost of approximately $6.12, combined with the lamination salvage cost of under $1 and the copper winding wire cost of between $29 and $43, the total material cost of a complete Shrock configuration flux concentrator generator built from currently available materials sits between $36 and $50. The $4 figure that frames this investigation reflects Shrock's 1991 material cost using ceramic ferrite magnets recovered from salvaged speaker assemblies at zero cost beyond collection labor, transformer laminations from a decommissioned farm welder at scrap value, and copper winding wire purchased as the single non-salvageable component. The ratio between that construction cost and Exxon's $55. $7 billion profit year has changed since 1991. The physics have not. Daniel Shrock's Holmes County installation has been generating continuous electrical output for 33 years. Vantris published his field documentation as a technical note in the IEEE Transactions on Energy Conversion in 2016. The note received 4 citations in the 8 years since publication. ExxonMobil's 2022 annual report does not reference it. The 41 state Public Utility Commission adoptions of IEEE 1547 that prevent legal replication of Shrock's installation in new residential construction have not been revised since their original adoption dates. The utility industry representatives who shaped those adoptions have not been required to explain the specific provision that extends certification requirements to non-grid connected systems. That provision has no engineering justification in the IEEE 1547 technical record. It has a financial justification that Exxon's 2022 profit statement documents with considerable precision. Leave a comment telling us what electrical load you would power first with a Shrock configuration flux concentrator on your property. Subscribe now, because what we document next is older than Exxon, simpler than anything in this investigation, and was generating free electricity on American farms before the first oil well was drilled in Pennsylvania in 1859. The industry that replaced it did not do so because it performed better. It did so because it could be metered. What cannot be metered cannot be monetized. What cannot be monetized gets written out of the building code. The pattern is always the same. The systems are always different. The next one will make this one look recent.